Okay. So one thing I just want to say to kick off, there is something that's going to be in your assignment, and it's actually 4.6, and it is quite, only an engineer could come up with this title for something in engineering. A couple moment. So you'd think you know what that means, but we're an engineering class, so turns out you don't. And the idea is really this. It's kind of, it comes down to just pure rotation. You're not even gonna, I didn't even assign any questions out of this, but it's something that's going to come up in your assignment, and you at least understand the concept of what it is. And it's kind of what you do when you're driving a car. In other words, if you decide you're going to turn, you don't want your steering wheel to translate. Like, I don't want it like out the window or up at the ceiling. So you pull down with this hand and pull up with your left hand. And so all that does is cause the steering wheel to rotate. So it doesn't translate, doesn't go anywhere else. So just so that you understand it, the reason it's couple is there's going to be a force going in this direction and the exact same force going in that direction. And that's kind of what you do, because if you did pull up with 100 pounds and you pull down with 50, then it's actually going to go up because they don't balance. But if you pull up with 100 and down with 100, then it's not going to move up or down. It's just going to spin. Does that make sense? So couple because, hey, look, two forces. And then moment because this distance in between them, notice it's perpendicular. And so here's something kind of interesting, and I'll just point this out really quick. The moment from this is just force times distance, like just one of those forces. And you might say, well, wait a second. I'll make a copy of this if I can. I can. So you might think to yourself, wait, that's not how you do this. And you'd be right in the sense that, isn't it going to rotate around that point right there? Like if that's your steering wheel, is it going to rotate in the middle? Like it's, so why would it be force times distance? It's not really force times distance. It's more like distance over 2 and distance over 2. Does that make sense? So if I called this A and I said, okay, what's the moment around A? Then you'd say, okay, cool. I've got sort of this force over here on the left, and that's a force of F, and it's times its distance of D over 2. And notice those are perpendicular, so we don't have to do this complicated vector business, and you know, it's not complicated for that reason. So it'd be that force, and that's causing, this one's causing rotation in this direction, which we said was technically negative. I'll ignore that for a second. But then, don't we also have this one over here? Which, oh, I guess that's weird. I guess it's actually also force times D over 2. Isn't that interesting? So sort of like this is this one, but this one over here is that one. So that's what you kind of think is going on, right? Well, let's do the math. Like if you added those together, then wouldn't you have, well, you have the same thing twice. So don't you have 2 of those? And then don't these 2's cancel and you just get force times distance again? So oddly, it turns out that if you have a couple of moments, so the key is these 2 forces have to be equal. If that's 100 pounds and this is 8 feet or something like that, in order for it to be, by your book's definition, a couple moment. Again, it's important that those are both 100 because then this thing isn't going to try to move up and down on us. It's just going to stay put. Then it is naturally going to rotate around that center point. But oddly, even though you'd kind of think, oh, we have to break this down and do it complicated like we just did a minute ago. No, really what this is saying is there's a shortcut here. In this situation, the moment by this shortcut is just going to be 100 times 8, 800 foot-pounds, if you will. That's how badly that steering wheel wants to rotate, so to speak. And so because so much in our culture is rotational, think about all the car parts of the engine and so forth. We'll talk about that a lot between this term and next term. Because there's so many things that are rotating and you don't want them like moving out of the car, so to speak, you want them to stay in the car, then this concept kind of comes up. So interesting. But let's dive into this first example 102 that I highlighted, because notice what it says. It says replace the loading system on the post by an equivalent resulting force. And so you'd say, okay, I know how to do that in a couple of moments. So, it's like the word comes up in there. So let's just figure out what's going on with that. Well, you should say, okay, cool. I see 3 forces going down. They're not all going straight down, but 650, 300, and 500. You should feel fairly good about changing those into one force. And so let's just stare at that for a second. But then notice there's also something else thrown in here. This guy. You understand what that's telling you? Because I don't think we've seen that before. So it's like I have 3 forces. Think of somebody is pushing on it, or somebody set a weight on it, or something like that. But then all of a sudden there's 1,500 Newton meters, and notice it's saying basically it's desired to rotate that way. Another thing that's weird about that picture is notice there's nothing causing that. Like, what's causing that? Well, there's nothing causing the 500 either. I mean, you just kind of imagine some of these. We're not kind of told where that's coming from. Basically, we're told there's 3 forces acting on it, and those are going to cause it to want to rotate, but they're also going to cause it to want to go down, right? It's going to want to translate. But somebody also has some force around A that's wanting this thing to rotate. And 1,500 Newton meters seems like quite a lot. So it's like this thing really wants to kind of spin like a propeller and really move. And so really what we're considering in 4.7 and 4.8 is both of those things at the same time. How does this thing want to translate? Where does it want to go? Because again, we're going to have to stop that. And we aren't even tackling this next, but you can see that there's a couple of supports on it right here and right here. And those are going to have to stop all this motion, because based on what that is, this is not a propeller to an airplane or the, rotational components of a car engine. Like, we don't want this rotating. We don't want it translating. That's supposed to just sit there, right? So we're going to have to, well, do what we're doing, resolve all of these forces into one force, and then know how it wants to rotate, so that then we can take one more step here in a couple of weeks and like make it not rotate and make it not move. And it'll be those 2 connection points that'll be what we'll tackle next. But at this point, we're just trying to resolve what does this thing want to do right now, thanks to all that stuff happening to it. And so the couple moment thing comes in, and really that's just a word that says, do you notice it's going to want to rotate? Even without that 1,500 on there, this thing's going to want to rotate around A. But of course, we're just not sure yet which direction. So a number of ways you could do this, but one of them would just be to say, well, I'm going to figure out what all the sum of the forces in, I don't know, Y. I see them all pointing down, and for some reason that stands out to me. So I'm not doing X first, I'm doing Y, but so what? Whichever one I want. I'm picking that one first. So the obvious one is negative 300, because I don't have to make any kind of modifications to that because it is already going straight down. Whereas the other ones I actually am going to have to modify. So that 650 right there is going down, but the vertical component of it, because of where the 30 degrees would be a cosine modification. Do you agree with that? I'm going to erase this, but again, if you're not super fast at trig yet, if this is my 650 right here, and this is my force in Y of that particular force, and this angle's 30, then wouldn't I say, oh, adjacent is f of y, 650 is the hypotenuse, so I'd say the cosine of 30 is adjacent over hypotenuse, and therefore I could multiply this up to this side to get the force of y. So, I'm proceeding to that fairly quickly, assuming you've suffered through a lot of math, and that isn't terrible, but to the extent that you need to, don't be afraid to draw right triangles and slow down until you're a little faster at this. So I like to think of it as modified. That's 650, but only the cosine of 30 of it is actually vertical. And then similarly on the other one, it's also down. I can see the arrow is aiming down, so I'm just doing that based on common sense. And then that would be modified. And notice the 30 degrees over here is actually measured from vertical, whereas the 60 there is measured from horizontal. So it isn't just always cosine and always sine. It depends on where the angle was given. In this case, I'm interested in the vertical component. Well, that's across from 60, so that makes it a sine modification. So do you agree that's the summation of all of the vertical forces? Now, again, as I said before, we're going to come back and say, well, look at A and B. There's attachment points there. And those could represent arrows pushing up, just like this floor is pushing up on that desk right now. And we could add those in and make that sum. We could make the sum of all those forces be 0. That's what we're going to want to do ultimately. But for now, we're just going to say what's happening with all of these. So I punch all that stuff in. And I'm going to get some cool negative number, minus 300, minus 650 cosine of 30, minus 500 sine of 60. I got negative 12, negative 12, 95.9. I'm going to call it negative 1296. I don't care about rounding, and I'm just rounding how I want. So this is the forces in Y. Again, this isn't the final answer, but that's kind of important. So say, okay, this thing badly wants to go down. And then let's reconsider what's happening in X. So notice the 300 we had a second ago, because it's straight down, it's making no contribution to X. It doesn't want it to go right or left at all, but the 650 and the 500 do. Now the 650 is aiming right, so by standard, and you'll see this some places in your book, like they'll even come in here and say, oh, by the way, up is positive, and over here they'll say, oh yeah, by the way, right is positive. But since that's kind of what we're used to with graphing or with graphs, I'll typically just do that and then leave that off. But remember, you actually don't even have to have horizontal and vertical. Like you can actually change some things at an angle. You could say, I'm going to call that the x-axis. So you can actually change the axis. Don't worry about that later. Anyway, 650 is obviously aiming right, but has to be modified not by cosine of 30 like it was last time, but the sine of 30. So that's how badly it wants to go right. The other one wants to go left, so I'm going to give it a negative sign, and it'll be 500. But last time it was sine, this time it'll be cosine to give me the other direction. And that's it. And so maybe at a glance, you're thinking, I don't know who's going to win here. Am I going to get a positive or negative answer? Which ones? Or maybe it'll be 0. Maybe there is no desire for it to go right or left at all. But when I say 650 sine of 30 minus 500 cosine of 60, I actually do get an answer to this. I get exactly 75. Last time it was approximate. I rounded off. This time I actually don't have to. So the sum of my forces in X is 75. If you're paying attention, remember that's a plus 75, so it means right, but it's never a bad idea to say, up, down, right, or left. But I'll just leave it like it is. And thus, if you were to kind of draw a picture of that, wouldn't it be? Notice I drew the negative sign here. I didn't actually call it negative. It's 1296 that direction, and if I draw my vectors head to tail, 75 in that direction. So then that would be my force resultant. So I just took all 3 of those forces, got rid of them, and now I only have 1. That's kind of cool because it'll make it a little bit easier for us to solve the problem here and make this thing not move. So does it make sense in vector form? You could say, hey, I'm done right now. 2 options: force as a vector. You could say that is X negative 1296, Y is 75. Notice I'm using the lazy terminology, not I's and J's. I'm just writing it as a vector. You could say I'm done. There it is. And if you let me, that's what I would stop at. And we have seen that's kind of a more useful way to record things. But if somebody wanted not the X, Y, the rectangular version of that, but kind of the magnitude direction form, we'd say, okay, I can do that. So the magnitude force R, of course, would be the Pythagorean theorem. That's right, Pythag. And by the way, get in the habit of doing this kind of thing just to make sure your rounding is accurate. Like I still have 1296 in my calculator, don't I? Why retype it and be wrong? Like why not just go back up and get it and say squared and then 75 and squared? So I'm going to go back up and get that. and it's still sitting there as negative. So I'm a little worried about squaring it. So to make sure I don't screw it up, I'm gonna go back and get rid of that negative. So I said squared plus, and I'm just gonna type 75 squared, square root that. I got 1298. And because now I actually have the resultant force. But then secondly, I'd like to know what direction that's going. And again, based on the pictures that I drew, you could just add your own angles to this. Like if I said, all right, I'm just going to call that my angle right there. So wouldn't that be inverse tangent? If I said tangent of theta would be 75 over 1296. Now, again, the question is, should I be using negative 1296 or positive 1296? If I make it positive, which is what I'm doing right now, second tangent of 75 divided by 1296. I got that theta is approximately 3.3 degrees. If I do that, does it make sense you have to rely on the picture of where I showed theta? Because remember, how do we measure angles? We measure them from there going that way for positive. So, really, I'm talking about being there, right? That's my force resultant. So, like, what's the real name for that? It's not 3 degrees. You can't just say 3 degrees with no picture if you're going to take the approach I'm taking. If we left the negative in there, I wonder what it would say. I'm going to go back and put the negative in there. I got negative 3.3 degrees, which doesn't look correct either. This is why this kind of could be confusing. Like, wouldn't this be negative 3.3 degrees? I mean, it's not very far, right? It's not down here. See, it's like not in the right spot. So if you draw a picture of it like I did, fine. Why didn't that work? Well, because if it's going to work kind of in this environment right here, like you got to draw it correctly. In other words, if I wanted theta, if I wanted that to be theta right there, and I'm not talking about the same right triangle that I drew over there. I just happened to do x first and then y. But over here, if you went first x, which is 75, and then y, which is 1296, does it make sense you have theta in a different location? I had it in a little skinny location because I wasn't paying any attention. I was just drawing the picture however the heck I wanted to. But if you wanted to match this, then you would say 75 and 1296. But notice now this is the opposite. So you'd have to say tangent of theta equals x is first, opposite over adjacent, 1296 over 75. And if you threw that in as a negative like it's supposed to be, then you would actually get kind of the correct sort of trig answer to this, where you wouldn't have to have a picture, if that makes sense. But I like pictures because I want to touch it and feel it. So again, that's just my temperament. So my point is, like, this is the kind of thing that you could get the right answer, but then look it up in the back of the book and it wouldn't agree, because it's not like their answer is exactly the same. In my case, because I said that angle right there is 3.3, then when I look in the back of the book, they might actually be giving that answer. And since this whole thing is 90, what is that? 86.7 or something like that, 86.7. Yeah. Like that might be what I see in the back of the book. And then I would just go, oh yeah, I got it right.
Shouldn't that be negative?
Yeah, and then it would be negative to say go backwards. But then, even then, if you drew the picture and said, hey, it's 86 right there, the picture would mean you don't need the negative because you showed it going that direction. And so again, don't change it. Don't think you have to get the same answers in the back, because there's a lot to this. So I'm done because my picture shows you where 3.3 degrees is. But I happen to know this particular one, that's not the answer that's in the back of the book. So however you slice it, I have the resulting force. I'm done. But then they went on and said, okay, let's have a nice couple moments. And notice, in order to decide how something is rotating, you got to decide what it's rotating around. And so they did say around point A. So what's happening? Now, here's what's kind of cool. You could have done this from the start. Does it make sense? I could have done this from the start, and I would encourage you to do this on the side. In the interest of time, I don't think I will, but I had 3 different forces. Do you agree that that 300 is causing no rotation around A because it happens to be pointing right at it? It's not that it doesn't have a force of 300, it's just it has a distance of 0. So I could have put the 650 in there and the 500 in there to see which rotation, and then don't forget the 1500, which is just magic coming from nowhere. And then that would give me the answer. But now that I've reduced this whole thing into just one force, they're like, those other ones aren't there anymore. Does that make sense? I could just put my one force in there and get the answer that way too. They're both the same. Doesn't matter which one. I just happened to do the translational force first. So what about moment? So now that I think about it though, does it make sense? I don't know where my force is. So that's going to be a problem, isn't it? Because I don't know what distance. I don't know what the distance is. I don't know where to put it. I can't just hang it. I mean, I could say, okay, I know where it's going, but does it make sense? Is it there? Is that where it is? Well, that's one distance, but what if it's over there? Well, then that's a totally different distance. So actually, maybe I can't do this just with my one force because I don't know what the distance is. Does that make sense?
You're talking about the 1500.
Well, that plus the 650 and the 500 want it to rotate around A too. Like everybody's kind of pushing on this thing, and so it wants to rotate. So I actually got to consider everything. So what is the moment? And again, it's kind of good practice to say the moment. Whoa, I'll leave it. A few too many hoops there. Around A, because you're telling somebody, you know, this would rotate different amounts around different locations. I can't leave it. It's killing me.
I love how it used to be that. I'll leave it. I can live with it.
All of a sudden I couldn't. I just couldn't live with it. But just like we saw before, does it make sense, given that this vector keeps going, does it make sense if I want to use 650, then that's my distance right there, which is painful. What's easier? Basically, break 650 into its horizontal and vertical components. Well, we already did that. Do you agree that this would be the horizontal component? Do you notice it's pointing directly at A, which means it isn't going to cause rotation? Whereas the vertical component right here is at a distance of 3 meters. And it's not hard to change 650 to its vertical component. And so this is the easier way to do this. So, and let's see, you should agree that that's causing rotation in this direction, which we said is positive. So I'll start with 650. Its vertical component we said a second ago was cosine. So 650 times the cosine of 30, collectively, that's my force, times 3, which is my distance. Force times distance. That's how I find desire to rotate, moment, torque. And so that's positive. So I made it positive. Awesome. So force times the distance. Cool. And then don't I also have 500 going, 1500, I'm sorry, going that direction as well from nowhere. You don't have to multiply anything. Notice its units are already Newton meters. Again, I'm being lazy and not writing this down, but wasn't that 650 newtons times 3 meters down there? So those are Newton meters too. It's not that I'm ignoring it. I'm just not writing it down because there's a lot of stuff here. So I'm choosing to take that approach. And then I got that 500 over there, but isn't that 500 sort of fighting this? It's actually wanting it to go in the negative direction. So that's kind of trying to stop this. So I'm going to, again, based on visuals, I'm going to say that's negative. And so just like before, this would be its vertical component. Its horizontal component would be coming in there, pointing right at A. Remember the bike, how the force was way up in the air, and so its vertical and horizontal mattered? Well, this one, its horizontal component is pointing right at A, so that doesn't give you anything. So the vertical component of 500 was based on the sine of 60. So 500 sine of 60. Again, that's the force. And then notice its distance based on where I drew it. Notice the arrows are in the same location. I can't draw it over here. Does that make sense? Because that's at a totally different location. It's contacting the beam right there. So its distance is 5. So there's all of the moments working together. So this is not going to be 0. Like this thing is going to rotate. And if we get positive, we'll know it wants to rotate counterclockwise. If we get a negative, then we know it wants to rotate clockwise. So I just get to type all that in. If earlier I had written down when I was using 650 times the cosine of 30 and stuff, if I had written that down back here, you know, that'd be nice because then I could just stick that in there and it wouldn't look so weird, right? 650 cosine of 30 times 3 plus 1500 minus 500 sine of 60 times 5. If I didn't type anything wrong, I got 1023.68. Positive. So counterclockwise, I'm just going to make a note of that to myself. I don't have to write that down, but it's just kind of important to notice that. So this thing wants to translate, it wants to move down and to the right, way harder down than to the right. And it also wants to spin on top of it. So wow, this thing's going out of control. So effectively this, and by the way, what are you going to see in the back of the book for that when you look back there? You're not going to see that. What are you going to see?
1.02.
Correct. Move the decimal point 3 places to the left, change newtons to kilonewtons, and then only 3 numbers would be 1.02. So your first instinct should always be like, oh no, I got it wrong. Oh wait, no, I didn't. I got it right. Cool. So based on what I said earlier, you should be thinking like, well, wait a second. I thought, you know, like a couple moments like this, right? Like one up, one down, and perpendicular distance. And so, you know, one of the things that bothers me, and it's one of the reasons I'm skipping over this pretty quickly, is like that's the answer in the back of the book to this, so to speak. But it's like, wait, where's the other one? Like, is there some other force of, didn't we say 1298 up here? Where's the other force of 1298? Well, keep in mind, what in an actual couple moment, what happens is there's no motion, it just stays in the same location. Later on, whereas this one goes down, right? We got forces pulling down and to the right. So this is not a couple moment. That's the moment. In a sense, I sort of, in terms of you understanding this, I wish they would have just said, what's the resulting force and moment? Just left it at that, because that's really what our answer is. Now, in reality, that's what you need to understand to get really 4.7 questions correct. You just need to say, hey, I know how to find moment and I know how to find resultant force. Let's just do it all in the same problem. There's really nothing new to learn here. All 4.8 does is say, okay, well, my good idea, I had this brilliant idea of 1298. I think I'll write this down here. What's 4.8 about? Well, here's A in this picture. And I now know that 1298 is in this picture somewhere, and we know what direction it goes, right? It goes like that direction. Isn't that the force resultant? But we don't really know where it is, right? So let me just draw a couple of those in. I'll draw one over here. Now think about this, because again, I'm interested in you learning how to think, not just get the dumb problems right. Based on this answer that you just got, one of those can't be the one. One of those is not it. Which one? And why? So we just got rid of all 3 forces and we just have one now, which is totally correct and totally true.
Would it be the one on the left? That's the force pushing the
This 1023 caused what direction rotation? It's positive. So it's basically trying to get it to rotate that way. So which one of those two, which side of that A does that have to be on then? To do that. Does it make sense? It can't be that one, because wouldn't that be spinning it the other direction? Would that be
But it can still
negative?
be- So that just eliminates half of our possibility.
Yeah, now we still don't know, like where it is exactly location wise, but we know it's on that side. 4.8 goes on and says, no, you can actually figure its exact location.
So what I don't get is we have that force, but I don't understand how we have that force and a couple moments. So like that 1023.7, is that like the resultant of force times distance? So like, are we spanning a distance of 3 meters plus 5 meters for both the moments? And then that's like,
Yeah,
so
well,
we divide that by, you know what I mean?
let's talk about that, because that bothers me a little bit too, to be honest. I actually don't feel super good about that. So we'll talk about that in 1 second. Would you agree that this force resultant we said earlier was 1298? But, and I'm drawing this too long just so it fits good, but wasn't that really 1290, approximately 1290? Wait, yeah, 1296 down. And 75, did I draw those in correctly? Like that's what's really going on there. So notice the 775 isn't causing any rotation because it's pointing right at A. But the 1296 is. So all 4.8 does is say you can actually even figure out where this thing is located. And now you might appreciate if you're trying to stop rotation from happening, like knowing where that force is really important. I mean, if I say, hey, there's 100 pounds pushing on this podium right here, it matters a lot that it's sort of on this side versus coming straight down on it versus here on the edge where it might break it, or versus over here, we'll tip it that way. So I'm saying it's 100 pounds and it's going this way, that's like it's here, here, here. So 4.8 just goes on and says, hey, now that you made those two calculations, you could actually use those to locate it. Does this make sense? Since this is, because I sort of got rid of the red force resultant and then just thought of the blue one, does it make sense that really is perpendicular right there? Therefore, that's the distance it is away from A, but notice I don't know what it is, but I do know it's on that side. But don't we know that 1296 times D has to be what? Doesn't it have to be that number that we calculated earlier, 1023.7?
Wasn't that our couple of them?
Well, that's the complete, I mean, irrespective of how you decide where to locate it, that's the desire that thing has to rotate. However it's rotating, whatever's causing it. Because again, like what causes something to rotate? I could push here on this desk and get it to rotate that way, but couldn't I also push here and pull here? And that's the idea behind a couple of them, is just to say, well, if you just want it to rotate, I can lift over here and it'll rotate. But that's also going to make it want to come up in the air. But if I lifted here and push down there simultaneously, then rotate like a propeller. Like it's not going to lift up in the air, it's just going to rotate like a propeller. Either way, it's causing the same rotation. So basically, a couple of moments saying, let's just think about rotation and not really worry, how is it rotating? What's it rotating around? And that's really the idea behind it.
I just would have put the force. That's what it said. We put the components, the X and Y components of that force, and now we're throwing the moment as the hypotenuse.
Yeah, because they are working together. Like it is that force along with that magical 1500 that was thrown in there, but it is those forces that's causing this rotation, right?
Well, it's just weird because we took the X component completely out when we found the moment, and now we're adding it back in.
Well, it's just that you can. That's what's so cool. I mean, the end result of this is we can actually not just say this is the resultant force, but we can even locate it because of this calculation. Do you see this? So roughly, if I take 1023.7, since I'm solving for D, I divide by 1296, I get 0.79 approximately. What does that mean?
0.79 meters away from it.
Yeah, notice I've been lazy. This is newtons, this is meters, this unit over here is Newton meters. That makes sense because it's newtons times meters is Newton meters. So if I divide the newtons over to this side, of course, those are going to cancel and I'm going to end up with meters. So that's like, oh, okay, that's not quite a meter, but it's a lot of a meter. A meter is pretty big. So that's like 3/4 of a meter. So I now know exactly where that thing is located. That's all 4.8 really adds to this. So let me attempt to answer. Answer your question now, Connor. So this is, I'll just write in 0.8 meters right there. So now that's exactly the result of all of this. And notice this picture isn't quite complete because I didn't say what angle that 1298 is going at like that. So the picture looks nice, but without that angle in there, maybe that's not perfect. We said that'd be 86.7, which is roughly 87 degrees. So now it's kind of complete. So I got rid of all the forces, all the rotations. There was magical rotations thrown in, forces going everywhere. Now there's like nothing. There's just one force now. But again, notice that's not 1298 times 8 meter times 0.8 meters. But if I was to go over to this side, I mean, I guess here's the question. If I was to go to here and redraw that exact same vector parallel, so those two vectors are parallel in the same exact length, that's also 1298. Does it make sense? That's the picture of the couple moment. And so the idea is the same with the steering wheel. It's like I could pull with 100 pounds up here and 100 pounds down there, and that'll cause rotation. But I can also kind of do that with one hand, right? Well, we just sort of showed one hand. So it's a couple moment because you can think of it as there's another one there that goes with it anytime you want to.
Would the vector be 0.8 on the other side? Or is it?
It's between them. Yeah. So that's the idea. My point is you only really need to see one side sign in this one side in this case. Okay, so to make this work out good, this one, I kind of drew my own picture for this. So this time I said replace the forces acting on this cantilevered beam by an equivalent resultant force and couple moment acting at O. And again, I won't probably use that language on a test. But then I said a second thing, which is specify where that is. Where is it? That's really all that 4.8 adds to this. So notice this has got 3 different forces on it. No magical moments being added to it. There's just 3 forces acting on it, 52, 40, and 60 pounds. One thing though that's really interesting, how come I told you that cantilevered beam sticking out? And also get to know the language of engineering a little bit. You see those kind of cross hatches over here? What's that telling you? It's telling you that that beam is attached to some kind of a solid wall. It's like, we don't know what that is. Is it steel or dirt, concrete? I don't know, but it's like there's something over there that's this thing's attached to. But in the last problem, all those arrows kind of pointed right at the horizontal line. Well, notice these arrowheads, if you will, are not. Like that's actually not pointing where O is. O is in the center. Now, just to also help you understand the couple moment thing, let's say that there, just to keep it simple for a second, let's say there was like one giant force up here pushing down. Does it make sense that the bottom part of the beam is going to kind of smash into the wall, if you will? What's going to happen to the top part of the beam though? It's going to pry away from it. So it's going to kind of try to do this. Does that make sense? So if I'm trying to get that to stay there, like that attachment to the wall is not just like, oh yeah, attach it. I mean, your job as an engineer is to put some bolts, some glue, something there that's going to keep the top from tearing away. That'd be tension, and then the bottom from crushing into the wall. And so do you see that as in a sense kind of like a couple moment? Like one force is going to be pushing this way and one force is going to be pushing that way. It's going to like a steering wheel rotating around that point. I mean, that's the idea behind a couple moment. So the big picture is like, get this thing not to move. Anybody been to the Grand Canyon? There's kind of a, I've never been there, but I've seen pictures of it. There's kind of a cool plexiglass walkway that sticks out over the canyon, because obviously it's pretty bad for customers if they're like here to the edge and look over. And in America, like they make it so you can't fall off like that. I was in Ireland and there was a place like that and you could just walk right up to the edge. Like I sat on the edge with my feet over it. It was like 1,000 feet straight down. Awesome. So it's like, that's kind of what you want, right? You want this cantilevered thing so people can walk out there. There's a railing around it. You can even just look through the floor because it's made out of plexiglass. And you can lean on the railing and nobody dies. So that's kind of cool. And so these forces would all be coming from the gravity and the people that came and went, they'd be live load, but then just the weight of the structure itself, just to hold its own weight out there. So these arrows, if you will, and we'll calculate those more a little bit later, are going to be based on, well, how much does plexiglass weigh? What does fully loaded mean? What's an average person? Like statistics, what's an average person? What if a bunch of heavy people get out there? And we've got to kind of load that thing up like completely full with the heaviest people that walk around, right? And then build a factor of safety on top of that so that even if they start jumping up and down, we're all good. So this is simple. We're just throwing these weird random forces in. There's only 3 of them. They're not continuous. There's like 3 people and they're pushing and standing really weird. But do you notice, for instance, this 52 pounds, wouldn't this be its horizontal component and this be its vertical component? Is this horizontal component causing desire to rotate around O? The answer is yes, this time it is, because isn't that 1 foot thick? And so isn't that distance right there, half a foot? It's actually causing rotation. We can't ignore the horizontal component this time because it's not infinitely thin. So we got to think about that. So it's like, where's that arrowhead is actually really important. Now you will notice a lot of times in the book, just to kind of make your life a lot easier here, they're going to take this arrowhead, and this is what exactly was kind of going on in the last problem, and the arrowhead will actually be right there, which means it is on that line right there. So the horizontal component is pointing right at O, and it's not going to want to rotate at all. Let's take a look at the last figure really quick. What did they do? Yeah, they put A up on the top, which is kind of weird because would it rotate around that? There's really nothing there. Wouldn't it rotate around this point right here? Wouldn't it be rotating around that? That's what it's sitting on. So if that was A down there, this would have been a more complicated problem. Do you understand that? Okay. So I'm going to kind of do what we did last time, which is figure out the sum of the forces in X and the sum of the forces in Y. I'm going to go kind of fast here. Sum of the forces in X. Again, notice, hey, 40 is going straight down, so it isn't doing anything. And then 60 is aiming right, so that's going to give me a positive force. But again, 60 has to be modified by what? The sine or the cosine of 40. Good job, cosine. Notice where I'm putting these. This is going to be the vertical. This is going to be the horizontal component. So that'd be the cosine. So it's modified by the cosine of 40 degrees. And then you got 52, but it's going left. So as I drew in a second ago, there's the horizontal component. There's the vertical component. So it's certainly going left. So 52 gets modified. I'll call it negative because I can visually see it's going left. But notice this time you're not given an angle. You're given ratios. And so what's its ratio? What ratio? Cosine of 40 is also a ratio. Yeah, horizontal to hypotenuse, 5/13. So this gets modified by 5/13. So cosine of 40 is serving as the ratio in one situation, and 5/13 is serving as the ratio in the other, and that's it. Now again, notice I oversimplified this because what other force is definitely there in the real world that's doesn't seem to be calculated here? Yeah, the beam itself has got gravity on it. It weighs a lot. So knowing the material, the problem with that is though, it's not just one weight. Like you don't say, oh, that thing's 5,000 pounds. It's 20 pounds per foot. There's hundreds of arrows up there. So actually the last part of chapter 4 that we're actually going to save till a later section because it makes more sense to come up later. We're talking about continuous forces, not just 3, but 3,000 of them. And how do you reconcile that? So greatly oversimplified. Anyway. Very well said. You're exactly right. And that's exactly why that's saved for later, because depending on how those forces work, you're adding up lots of things. You have no choice but to use calculus. So integrals add up lots of tiny things. So they'll take care of that for us when necessary. So let's see, I got some of the forces in X. It came out positive. I got 24.3. Again, I'm just choosing to round that off. And I see all those units are pounds. So the end result is, oh, I just learned this thing is trying to be pulled out from the wall. You see why that's important? Oh, it's trying to be sucked away from the wall. Okay, that's different than being pushed into the wall. So that's just good to know. Same thing with Y. I got 40 going down, straight down, so it needs no modification. I've got 60 going up, but it's got to be modified by the sign of 40 this time. And I got 52 going down, so it's going to be negative. And it's modified by the vertical component over the hypotenuse. And so there's the sum of all of my Y forces. Could have punched the button wrong, but I got negative 49.4. Cool. So apparently this thing wants to go down and be pulled away from the wall. Awesome. So in the language of math, this is how this thing wants to translate. Is that right? Translate. No, that's not right. Translate. Yeah, that's right. Translate. This is the translation, which basically means moving up, down, right, and left. But secondly, the other type of transformation in math is called a rotation. That's the two kinds of basic motion. The third is scale, like something can get bigger or smaller. It can spin, it can move, it can get bigger or smaller. That's the three things it can do. So of course, rotation means spinning in circles. Okay, what happens there? Well, again, like before, I've got to figure out, and again, you'd be inclined to miss some of these. So what is the sum of the moments around O? Well, I've got 40, and notice it's perpendicular to 6, and so 40 and 6, no problem. What's wrong with what I wrote here, though? That's not a factor here because that 40 can kind of be anywhere on this line. But what direction is it sending it, positively or negatively? I got to think about that. Yeah, and again, it's never a bad idea to kind of write that stuff down, like I said over here, you know, to the right is positive, to up is positive, and then over here, if I want to find the sum of all of these moments, maybe I'll write the sum of all those moments. I could, you know, write a note that says, hey, I'm going to use the standard notation that that's positive. So because those are standards, you don't really need to write them down. But you could actually turn those backwards if you wanted to. So anyway, because of that, that makes that negative. So that takes care of that. Awesome. And then I've got this H right here, which I'm redrawing over there, this H. Notice it's a distance of 1/2 foot. And so that's actually going the other direction. In other words, it wants it to rotate this way. So that's actually a positive. So I've got the horizontal component of that would be the cosine like we used earlier. So it's like that answer. So this is 60 cosine of 40 is the same 60 cosine of 40 we had up there. That was the horizontal component of this. But moved over here, as I said, can you see that it's only a distance of half of a foot? So I won't write this everywhere, but again, that's the force and that's its distance from O. It is, that arrow is a distance from O. But then you also have this vertical component here, which we had down here. That was 60 sine of 40. And notice its distance is 6 and 4, 10. Again, I'm noticing feet, pounds, everything is feet and pounds. Okay, cool. So my rotational units will be foot pounds. Is that positive or negative? What direction is that rotation caused around O? Can you visualize it? Do you see that as causing rotation this way? Therefore, that's actually positive. Again, if you mix that sign up, game over, like you're going to get this wrong. Because the fact that some are working one way and some are working another has got to be considered. So collectively, this is all the stuff that's happening thanks to the 60. Now we move up to the 52. And so again, I've got issues here. So the vertical component we said a minute ago, vertical was Y, like this was the vertical component of Y. So that's still going to be 52 modified by 12 over 13. That's its force. But given that this is its vertical component, then I can see that, oh, that's 4, 6, and 2, that's 12 feet away. But again, is that positive or negative? Is it causing it to spin clockwise or counterclockwise? Because it's pushing down, it's sending it that way, which we're calling a negative. So, okay, I got to put that negative in there. And then finally, we have the horizontal component, which we used up here, 52 times 5 modified by 5 over 13. Again, it's easy to think that's right there, that is already moment rotation, because don't you have a force times the distance? No, that's a force modified. So that's still just a force. How far is that away? Well, again, this horizontal force is right here. I could think of it as being right there. So again, it's only half of a foot away. And that's causing rotation in this direction, which we actually call positive. And so that's positive. So interestingly, those two, the horizontal and vertical component just of that force alone are fighting against each other. Now you can probably appreciate when you take 52 and you basically don't modify it much, that's almost 1, and then you multiply it by a big number. This is having a lot of effect. Whereas 52 multiplied by a fraction that cut it in half, and then multiplying by a tiny distance, we're not going to get a lot of rotation out of this. But they're fighting against each other. So again, in the real world, if this comes up anything other than 0, everybody dies, right? Like this can't be rotating. Rotation is motion. Like this is the extension out over the Grand Canyon. We don't want this thing rotating, so we're going to have to make all this equal to 0 at some point. And if I want to see if I have this written down already, I don't want to type all that in. Waste your time. Sure, I did this some other time and had the answer written down. I don't. And also on a test, you can appreciate that's a dangerous business right there. Like write that down really clearly like that. And then if your answer is wrong, then I'll just know you typed it in your calculator wrong. It's not that big a deal. So, and I even go to the trouble sometimes of like, because you'll not even be able to read your own writing sometimes. Like I'll think, well, they're 9, there doesn't look like a 9, it looks like an 8. I wonder if they typed an 8 in, and I'll type the whole thing in, and if that's the answer, then I even know what you did wrong, and it allows me to give you even sort of more points and tease you also. So I'm a little worried about getting this wrong myself. Again, the good thing about your graphing calculator is you can see every single thing you're typing, therefore you can kind of tell if it worked. By the way, why did I pick such a weird number like 52 for pounds? Did you anybody happen to see that? $52 divided by 13 is 4. So those are whole numbers if you did work it out. So I'm very concerned that this is wrong, but I got that the moment around O is approximately negative 397.3. Oh, yay. And so we know what's happening. We know exactly what all of those forces are doing to this thing now. That's what's kind of cool about this. We found the result in rotation. We found the result in translation. We know exactly what's going to happen. Cool. So effectively, we're done with this part. And as I said before, isn't it okay to stop right there? I mean, in one sense, if the back of the book, I mean, and by the way, these questions in the back of the book, they probably won't stop there. They'll go on and find the angle and so forth. But there isn't anything in that problem that said you had to do that. I found the resultant force. There's its X and Y component. So here's the interesting thing. Which way does that thing want to go? Because of the negative 397? It does want to go down. Does that make sense? Which sort of it feels like it would do that. But remember, you're thinking about gravity. There's no gravity in this problem. You got 60 pushing up and 52 and 40 going down. Since 52 and 40 add up to 90 and 90 is more than 60, it kind of feels like it would go down even before we made any calculations. So if that's the case, then, where's this resultant force? Well, let's kind of draw it in over here. I'll just take a stab at it. Maybe I'm wrong, but. So there's I should be doing this with the right colors. So here's the 24.3 since it's a force in X. And the green was negative. So perhaps you can notice I drew it negative. I didn't call that negative. I'm going to do the same thing I did before, which is say, okay, well, I can do this in my, I'd rather draw pictures and kind of do this in my head. So if this is 24.3 and then this component is, notice I'll draw it a little better, double that, 49.4. So I'm going to call that theta this time. Notice this time I did X first and then Y, whereas last time I did Y and then X. And so this time the theta is kind of laying against the X axis, if you will. So now I can say that theta would be the inverse tangent of opposite over adjacent. Second tangent of 49.4. And I did round all this off earlier, so I'm not going to get as good of answers as I could have. But I got about 63.8. And I'll write this a little more carefully. And the magnitude of FR, thanks to the Pythagorean theorem, I'm not going to write down what I do here, but the Pythagorean theorem of 20.24.3 squared plus 49.4 squared, 55.1 approximately. So the question is, you think about this for a second before I just do it. Where would that be? Now that I kind of know everything, I know how badly it wants to rotate.
Negative 63 degrees. X-axis.
Yeah, so if I look this up in the back of the book, I might see negative 63.8 because that's from the x-axis and then in the negative direction, right? But my picture shows where theta is, and so there's nothing wrong with what I wrote either. So I'm doing it sort of visually.
True to file. Why? Why?
Yeah, so notice I know, I mean, I could draw the 55.1 pounds in there. Maybe I will. And since that angle 63 is kind of so big, I'll try to draw it accurately. So it'd be like that. So that's where it is. But in terms of calculating its location, remember, I don't want the perpendicular distance. I don't want to have to figure out that distance right there because that'd be the perpendicular distance. So I don't want to use 55.1, just like last time. I actually would rather use 49.4, which I was calling green earlier. But then think about the 24.3. What is it doing? Notice where I drew it very carefully here. Notice I drew it right on the center line, which means the 24.3 isn't causing any of the rotation. And it's kind of important I did that because if I put it up top, I'd have to consider 24.3 and 49.4. But if I draw it right there, let's see, and how did I word this question? Specify where its line of action intersects the midline. Actually, that was me hinting at you. Don't just put it up on the top of the beam or on the bottom, because then all of a sudden it gets really complicated. So I purposely put it in the middle because now I can say, oh, okay, cool. If this is my force, 49.4, then that's my distance right there. And since I know that moment equals force times distance, I can say, cool, I calculated the moment earlier as negative 397.3. And it's optional whether I include the negative or not. I could say, I see it all in front of me. I know 49 is down. And my force is that 49 right there. And I could assign a negative to that as well. Does it make sense if I do that, I'll get a positive distance? So if you're a person that likes the symbols, you'll get a positive distance, and measured from O, that would be positive because it means going to the right. In my case, I'd be more inclined to have not put any signs on that at all. But now you can see, oh, I take that moment of 397.3 and divide by 49.4, and I now know the distance, 8.04. So when you're all finished, in a sense, you have the black drawing. You have the 55.1 pounds, not degrees. You have the 55.1 pounds down there, and you even know what angle it's sitting at. And so you don't have all these forces anymore. Just have one. Now, if it was pure rotation, does it make sense, according to the kind of the couple moment idea, that this would be exactly the same force and those two are parallel to each other? And that then would cause rotation, if you will, pure rotation. But again, my argument is, and I will say this, the reason that this is kind of thought of as a couple moment is, does it make sense? This thing is going to go down and start rotating, but in order to stop that rotating, does it make sense the wall is going to have to be responsible to do what the red one does right there? We have to attach that to the wall in such a way that that counteracts all of that. And part of the reason why we know that angle is 63 degrees is so we can sort of go over to the wall and say, okay, wall, you know, you got to make sure this thing kind of doesn't spin now. So the wall is going to have to defeat the desire that this had to rotate this way. The wall, and we'll be adding these to our figures later on in this class. We're going to come over here and say, okay, the wall's got to be able to handle 397 of desire to rotate in the other direction. It's got to defeat the 397 that we saw over here. So the wall is going to have to do that. And then does it make sense if I draw this 55.1 exactly parallel to the other one in the opposite direction? That defeats the 55.1 in terms of up, down, and right and left simultaneously.
Wanted to not have people fall into the Grand Canyon, you'd make that 55 really high.
Well, yeah, I mean, we would say the wall has to be capable of that, and it's perfectly fine if it's capable of more. Because remember, the wall's not over there just pushing; it's pushing in response to what's being pushed on. So it's like people get on it, more people, and the wall is just like, I can handle that, I can handle that, I can handle that, and then suddenly I can't handle that. Down they go. So it's more like what the wall is capable of. So that's what couple moment really gets at in this idea is we got to defeat that. We can't just stop. We'll be doing that later. Okay, so you try the last one. I'm going to give you some time. This is more of a book problem. Wait, which one did I give you? No, that's not the one I gave you, is it? I gave you a different one. That I didn't put in here. Yeah, the one that I gave you is the one I wanted to do, so work on that one. I like this problem a little bit better just because you can actually see down at A, you can kind of see the base bolted to the ground. So you can see this thing being pulled on from different directions, guy wires pulling on it and so forth. You can see this actually doing a job, like attached to a ski lift or something like that. And net result is, how does that thing want to spin and how does it want to move up and down? And then I'll put bolts down there on the ground into the concrete in such a way that it can't do what it wants to do. That's right. Just as a point of learning, Nook, this time, in terms of the picture I drew, you're not done yet, I know, but this time I actually I broke the 500 and the 250 into its components and actually calculated what they were. And they're rounded off. Actually, I think 433 is the only one that's rounded off. But notice I kind of have everything's converted into its components. And so it's really going to be easier. And I also drew them correctly. I even drew them the right length so that they reached out to, match the end of this. And this went up to match the end of that. This went over to match the end of this. This went down to match the end of that. I kind of drew them correctly. So they should even look proportionate.
Did you do that because it's literally only asking for the line of intersection? So you don't need to do all the forces in X, forces in Y.
Well, I do because it did still ask for the resultant force. But it's just going to make, now that I did that, it's going to make my work really fast. So now that I did that, I can look over at the figure and say, okay, we got a negative 433, we got a negative 300, and then we got a positive 200. So one thing about this that's kind of weird is, notice it says specify its location measured from point B. In other words, like if I'm looking at this picture, I'm thinking it's rotating around A. Did you notice that? Like, I mean, it's a post standing up in the air. It's not going to rotate around B. That's kind of dumb. It's going to rotate around A. So should I assume that? Am I supposed to be smart enough to stare at this and go, it's going to rotate around A and that's the way I do it? Or do I go, well, it said rotate around B, so I think I'm going to go ahead and calculate the rotation around B.
Well, it wouldn't, I guess the vectors wouldn't make a difference, right? Like you're still gonna have negatives where negatives, positives. So 300 will still be going in the negative direction. So right now we haven't really specified, right?
Yeah. Interestingly, it will turn out that it won't matter. Now, if I figure basically, and this was the couple moment idea also comes into play, and why that's a thing is because this thing wants to rotate. And if we think of it as rotating in space, and not, we don't worry about the fact that it's flying, but it's also traveling downhill. We just think of it as spinning, and right now we'll just keep it right in front of us. It can rotate around any point it wants. It doesn't actually make any difference. We'll get the same answer either way. The downside, if we say around A, which is kind of what I find myself wanting to do, because that's what it looks like I see in the picture, is the distance I get is going to be from A, and it said, no, I want the distance from B. And you can see I stole this one straight from the book. So this, again, I find those directions a little weird. If I was asking this problem, I would ask it around A, just because that's common sense what's kind of happening there.
You enjoyed all that detail with the bolts around A, we're not even rotating around A.
Right. So yeah, it's kind of weird, and it would never rotate around B. The B is not stuck to anything. So if something's rotating around B, it obviously means that's staying still and the whole thing flies around it. It's like, well, what's the Earth going around it then? I mean, what's that thing attached to? Doesn't make any sense. Either one works. But I'm going to go around A just because it bothers me to do otherwise.
So would we get the, next we didn't get the same answer, because that one, the like 251 would be. Away.
Yeah, so take a look. Did these attachment points bother you at all? Do you notice that? Because I sort of purposely did something wrong here just to see if you would notice it.
You mean how you're like.
I mean, you see how this rope or cable or whatever is attached right there. It's not attached. It's not attached clear back here, like at the middle where I drew it. See what I'm saying? So really that belongs right there, doesn't it? This belongs up here. The answer is yeah, which is exactly why they gave me that 0.2 right there. Because like the beam I just drew a second ago, that force is not in the middle of the beam. Because of the way that's attached, it's actually that 250 is causing rotation. Do you see that?
I missed it.
Well, I purposely deceived you, so you should miss it.
Thomas says, I feel like we're racing it. That will be incredible.
Your favorite.
So this is the advantage of, because this is going to look nicer than what I did a second ago. Just because I already have the horizontal and vertical components for this. So I'm going to do the sum of the moments around A. And all right, here I go. So I got 300 times the distance of 1. So it's a lot easier to see the force in the distance now. And again, that's causing rotation in this direction, so that's actually positive. I'm gonna go ahead and put a positive in front of it, just to kind of help myself keep track of the fact that it's like, I don't want to screw this up. I gotta call this positive, and I gotta call this negative, and I gotta make sure I don't mix up that. So there's the 300. And then I got 433, it's going also in the same direction positively, even though that, again, the 433 is aiming left, but it's causing positive rotation. And 433 is a distance of 2 meters. And then I've got that little 250 there, which is actually going negatively. But it's only at a distance of 0.2 meters. So it's really small. And then I've got that 200 on the top, and it's causing negative rotation. And it's a distance all the way from top to bottom, so that's 3 meters. And then finally, I've got that 150. And that 150 is a distance of 0.5 meter. And let's see, it's causing negative rotation as well. You agree with all those? Is that what you were getting? I don't know if I gave you enough time.
So Doug, out of curiosity, if we did the moment around point B, we'd have different numbers, but would we get the same moment?
You'll get the same, yeah, you'll get the same moment and you'll get the same distance, oddly. Again, that doesn't feel like it, right? It doesn't feel like you would. But notice the 300 is really close to A, so it won't give us that much moment, but it's pretty far away from B, so every one of them will have like a different contribution now.
And then it would still be on the same location from the AB.
Yeah, so in my case, in a sense, I'm going to end up with a distance from A, but since from A to B is 3, if the distance from A is 0.2 or 0.7, then I can figure out the distance from B and just, oh, okay, they wanted the answer differently. I would highly encourage you to calculate the moment around A and B and see if you get the same answer. And again, that's the idea behind a couple moment. This thing is rotating, and it's going to rotate in space. If I throw this pen in the air and spin it like this, it's got a certain amount of rotation irrespective. And you could visually, you see it as spinning around its center right here. But does it make sense if you had a camera that would freeze it, and like the camera followed this endpoint? You could actually be led to believe, if your frame of reference, if you're standing on this end right here, that you would see it as doing this, even though to you and me, from our frame of reference, it looks like it's rotating around its middle. You see what I'm saying? So this is like very Newtonian and confusing, and so that's why you actually get the same answer either way. Since I see, I hope I got the same answer I got before, but I'm looking at an old note to save a little time here, and I see that I got 441 Newton meters for that. And perhaps it's important to point out that that's positive. For some reason, I find myself not trusting that. I did get a different answer. No, I didn't.
Okay. 441.
So again, it's kind of important to understand, or at least maybe note, or it's positive, so automatically, but it's going to be going in that direction. So that is its desire to rotate. So now I kind of got two choices really quick. I could just say, well, they said from B, so I already know that's the answer around, no matter what point I rotate around, that's its rotational component. So I could actually just go back to B and say, okay, well, if B is up here and it goes down here, notice my force in Y is straight up and down. So the force in Y is not in this, but 533 is in this. And if I'm rotating around B, let's see, around A, this thing was trying to go this direction, right? counterclockwise. And for some reason, I don't really trust myself. So if that's the case, the fact that my 533 over here from up above right there, the fact that that was going left, I found myself going, oh, okay, that's good, because it was going positively. And so this distance then is what I'm after, since that's perpendicular. And again, do you see why because it said intersects the post AB. AB is right down the center of that. So that means that 100 from up here is going to be right on that center. Therefore, it isn't going to contribute anything. So without, this time I'm going to ignore all the numbers. If I take 533 newtons of force times distance d, then I better get 441. So 441 divided by 533 is 0.83. But that's this distance down here. So exactly. So in my problem, I would have said around A. I would have said around A and 0.83 meters and we'd be done. But since they said, oh, we want it around B, okay, fine. 3 minus 0.83. Guess that's 2.17. Fine. So it's interesting. Let's see, if it's rotating around A, then this thing's going to want to go that direction, which we call positive, right? But if I think of it as rotating around B, then it's going to go this direction around B, which we call negative. Does that bother you?
Well, isn't it like this with the right hand rule, if it thumb's going down? So wouldn't that still be positive?
Yeah, I'm having
Yeah,
to,
that's out there.
that's bothering me a little bit, so I'm asking the question. So from time to time in this class, I'm going to give random extra credits. I need to shut up because I'm way over time, but for one, go find the sum of the moments around B. See if it's also 441. And then what about that seeming contradiction? Because I mean, this is genuinely bothering me, so I'm asking the question. If I throw this pen in the air and kind of spin it toward me, so it's kind of spinning like this, right? Again, what it's really doing for my frame of reference is spinning around the middle, it's spinning this way. But the question is, if you're standing here, if you're standing on this and it's spinning, so you're standing here, like you are on the earth, like right now you think, oh yeah, I'm always right side up, but you might be upside down on the earth right now. You realize that relative to the earth, you always think you're upright. But if you're standing on the top of this thing right here, and this thing is spinning this way, what are you seeing? Like I'm standing off here to the side going, oh, look at that, the thing is spinning. But if you're on the edge of this, what do you think is happening? You think you're still, because you think you're still right now, right? But you're really going 66,000 miles around the sun and spinning on top of it. So you're in a lot of motion. But if you're standing on the edge of this pin right here, you actually think you're standing still and this thing is spinning, right? So if it's spinning this way, from my perspective, standing back here, I'm like, oh, counterclockwise or whatever. What is this person seeing? Is it the opposite? Like, think about that. I don't want to answer it. Are they seeing it as like opposite as a result of that? Okay, so I'm going to show you an application of this tomorrow. This is extremely cool. It's kind of our first project we're going to be working on in class. It's entirely just using. It's an application of this right here because again, this looks pretty sterile. But I'll say this real quick. This is a big part of what I do in construction. Put a retaining wall right here. so that people can drive their cars kind of on this side. And then you pile a bunch of dirt back on this side. So it retains all that dirt. But do you agree that dirt's pushing on that wall? So unfortunately, that wall wants to tip over right here, and you don't have to drive around too far to see that, like it's all over the place. Meant for people try to do that. But if it's real important, like this is a, you know, a building or something like that, like we gotta keep that from happening. How are you supposed to stop that? Like if that dirt's pushed back? I'm gonna show you the actual calculations, the actual numbers from an engineer. This is something I get done on every other house. I can't stamp it because I don't have the certifications, but I do understand the math behind it. So I'm going to show you how to figure out how much does dirt weigh and how much it will push sideways. And we're going to talk about how the house, you know, what pushes back against that to keep that from happening. So pretty cool. All right, cool. So you might have some homework for me now that I'm sitting here. Yeah.
Use the email